Tonight I'm going to talk about global warming and global food production, climate warming, global food production. The projections for the next 35 years that we're going to have to double the world's food supply, mostly grains, to meet the demands of a growing population. To do that, we have to increase yields at a rate that was only achieved once in human history for a 20-year period at the end of the Green Revolution. We also have to do it in the face of stresses that were not existing during the Green Revolution, okay? Land. Pretty much up through 1960, most of the increase in food production was you just clear more land. You have great land out there, good soils, you clear more land, you can grow more food. Since about 1960, we pretty much used all the land that's good agricultural land. And in fact, we're losing that land at about a rate of 1% per year due to soil erosion, wind erosion, and salinization associated with irrigation. So increasing the land that you're producing food on is not really an option. Water, already limiting in a lot of areas, including here, I suspect. And I should say in the Green Revolution, there was 3 ingredients: better genetic materials, new genetic materials, increased irrigation, and the other one was energy and nutrients. In particular, nitrogen that came online pretty inexpensively. Well, nitrogen is more expensive. The other limiting nutrient is phosphorus, which people estimate has a world supply left of about 50 to 300 years, depending on how you count. So we have 2 stresses there under nutrients. Energy, during the Green Revolution, was incredibly cheap. It's relatively cheap right now, but not compared to the Green Revolution. And of course, it's going to get more dear as the economies pick up again and people use more energy. Energy is important because, in part, you create nitrogen from a process which is more complicated than I understand. And it's also cheap to pump water out of the ground, which is a very expensive thing to do. So it was important for the irrigation. The other part, which is new, is the climate is changing, and as I'll talk to you today, the climate change is introduce an additional stress in this. This is a measure of carbon dioxide measured in the atmosphere from 1958, when I was 2 years old, to last month. And it's just up, right? With little oscillations, which is basically the planet breathing. It's the plants growing in the spring, taking carbon dioxide out of the atmosphere and giving it back in the fall as the leaves and stuff rot. And then there's this trend, okay? We measure carbon dioxide in terms of parts per million. If I grab 1 million molecules of air here, and I count up the number of carbon dioxide molecules, when I was 2, it would have been 316, and today it's 400. It's increasing today because of burning of fossil fuels. There's lots of ways you can prove this is true. No one contests this number. About 90% due to the burning of fossil fuels, coal and oil, and about 10% due to the land use change, clearing forests, right, where you lose the organic material and the carbon locked up in trees and replacing them with fields. It's increased 25% since 1965, 10% since 1995. And you can see there's, there's a little bit of an upward trend here. It's not linear. It's increasing. The rate of increase is increasing. Now, not all places have warmed equally. So the world average increase is about 1 degree Celsius. But if you look at this plot here, you see that the continents in general, there's a little bit of purple up here, right, which is almost 2 degrees. And there's a lot of reds, and the oceans are kind of more oranges. So the land warms more than the ocean. The Arctic is warming faster than, say, the tropics. All these things are exactly what you expect when you increase carbon dioxide in the atmosphere. So not just the global average temperatures increase, but the pattern of change, the spatial pattern of the trends is exactly what you expect when you increase carbon dioxide. The other thing is, you don't have to believe the climate models if you don't want to. The glaciers worldwide are retreating. There's only one way to explain that. The planet's got to be warmer. Okay, for reference, I just showed you that we've gone from 320 to 400. 800,000 years ago, we know this. You can go down to the ice and pull out air bubbles and just measure how much carbon dioxide was in the air 800,000 years ago. And you find out that it's been going up and down, up and down, up and down. Each one of these downs is an ice age, where you have 3 kilometers of ice sitting over northern North America. And each one of these ups here puts us at about 260 or 280. And here's all of human history, basically, of agricultural history, from the beginning of agriculture to present, where carbon dioxide basically was around 280. That's where we are today. Okay? Atmospheric carbon dioxide. If you look at it, we only have ice cores that go back so far, but there's a lot of strong evidence that carbon dioxide hasn't been this high in at least 3 million years. The other thing that we don't know is that it's mainly this high. It's gone up over the 20th century because of burning of fossil fuels, mainly, and some to scent land use, clear land. The rate of change is 100 times faster than nature. We know what nature can do. The rate of change in this last 150 years is 100 times or more faster than nature can do it. And the time it takes to restore, if we just stop emitting everything today, CO2 to pre-industrial levels back here, is on the order of thousands of years, okay? So once you put it in, basically, it stays. I mean, it's there. You're stuck with it. The other point I want to make here, and I'm not going to go through the slide, is even if we know exactly how much CO2 is going to the atmosphere, if you give it to all the climate models that all do the same pattern of warming, land warms more than ocean, high latitudes warm more than tropics, but the total average warming will be different from one model to the next, okay? Okay, with a climate model. So here's the picture of the global average temperature increase. The global average is 2.8. The point here again is, as I said before, it's not everywhere the same. Land warms more than ocean. The Arctic warms the most. And the other thing I want you to take away is that the numbers here over land are more like 3 or 4. So if the global average is 3, basically multiply by 30% more to get the land average temperature change. Now, when it comes to precipitation, what do I want to say about this? The red, the deep red with the black dots on it are places where we're pretty confident are going to get less rainfall. The other places we see increases in rain are the dark blue places with the spots, which are like coastal Alaska, maybe Scandinavia up there, in places where nobody lives, okay? Other projected changes, just really quickly. Heat waves and droughts will become more severe in both their length and amplitude. By 2100, the global average sea level will rise by about 20 inches, right? And that's mostly because if you heat water, it expands. And if you expand water in the ocean, it's got to go somewhere and it goes up, right? But there's also melting glaciers, and there's also the net loss of mass on Greenland and Antarctica. So by 2100, the surface ocean will be about 3 times more acidic than the pre-industrial ocean. These are all things that are really well understood and kind of unavoidable. After we stop emitting, the climate will continue to warm for many centuries. It's something you can talk about over coffee afterwards. Okay. And therefore, sea level will continue to rise for many centuries. It'll take many thousands of years for nature to kind of restore this back to pre-industrial levels. Okay. Let's talk about, before I run out of time, impacts on food production. Okay? Precipitation. Like I said, there's not much we can say. We know there's a place in the world where it will be reduced. Here's Scandinavia. Here's kind of the Arabian Peninsula, the Horn of Africa, India. And what this shows here is how the wintertime and the summertime rainfall will change at the end of this century compared to the end of last century. These darkest black here, 50% reduction in rainfall. This is the wet season, by the way, in this region. And here's like 20 to 30%. In the annual mean, you're talking about a reduction in rainfall about 20 to 30%. For reference, the Dust Bowl was about 7%. Okay, so this is huge compared to any human experience. And it happens every once in a while for short periods of time, like it did at the end of last century. There was a 3-year period where there was a 30% reduction in rainfall in the stands. Okay? Iran, Afghanistan, Pakistan, Tajikistan. Right? all this arc here, about 20 to 30% reduction. And if you look at what happens there, in Iran, 80% of the livestock was lost and 30 to 75% reduction in wheat and barley. Afghanistan, again, you're talking about like 50% of livestock lost. Okay, so here's again a picture, the same picture, only just for summertime, northern hemisphere. I show this because the average crop grows for about 3 months. So the 3-month average temperature change, increase at the end of the century, under this split the difference emission scenario, is about 3 to 4 degrees. Okay, so the crops will be grown on average 3 to 4 degrees higher temperature. Okay, so nature's actually done this for us. France, 2003. Anyone remember this heat wave? Okay, the average temperature over Europe for the whole summer was 3.6 degrees, which is right what we expect at the end of this century. Right? If you look in France, well, it killed about 30 to 50,000 people in France and Italy. Italy, third drop, 36% drop in the maize yield. France, 30% decrease in maize yield. 25% decline in fruit harvest. 21% reduction in wheat yields. Right? If this was due to precipitation, this would happen every 3 years. This was pretty much a normal precipitation year. This is all heat stress. Okay? So by 2100 years of similar temperatures will be the norm. That's the most likely scenario at the end of the century. And I just calculate, okay, what does that distribution look like for 107 summers at the end of the century? And that's what it looks like. So we know this already. The most likely scenario is it looks like 2003. And there's like 1 chance out of 100 that it's going to look normal. And there's also 1 chance out of 100 it's going to look like 10 degrees Celsius above normal, which puts you dead center in the middle of the Sahel. Oh, sorry, the Sahara. Sahara, yeah. Okay? This isn't good if you want to grow crops in France, okay? Or even live in France, actually. If you do the same thing in the deeper tropics instead of in France, well, the tropics are famous that they don't have any variability in temperature, right? So a really cold year was a half a degree colder than normal, and a really warm year was 0.75 degrees above normal. And here's what the distribution like in the future. What are the odds that the temperature at the end of the century is going to exceed the highest temperature ever recorded? 100%, right? The odds at the end of the century that even with this kind of split the difference emission scenario, even with the wimpiest climate model that gives you the smallest climate change with increasing CO2, the odds of exceeding the highest temperature ever recorded is 100%. The map here is just a color and just says, what are the odds that your place in space is going to exceed the highest temperature ever recorded in the summer? And if you're red, you're basically close to 100%. And you can see pretty much everywhere in the subtropics, north and south, the odds of being out of bounds, something beyond anything ever recorded, is pretty much 100%, even with a split this difference emission scenario in a wimpy climate model. Okay, what does this mean for food security? This is a plot of temperature. This is actually Yaqui Valley, Mexico, just south of here. I don't know how far. I went there once by plane, and actually a couple times. It's the home of the Green Revolution, where wheat yields went from 1 kilogram per hectare to 3 kilograms per hectare. And this is just a measure. So this is controlled environment. It's irrigated. It's got plenty of nutrients. It's got way too much pesticide, actually. And this is just a measure of what's happened there in these controlled environments where the plants have everything they need in maize. And you can see each one of these dots is a year. So basically, you just see this trend. The growing seasons that are cold have 6 tons per kilogram, and summers that are really hot have 4.5. And it's a pretty nice line, right? The effect of fit is 10%. So for every degree C you reduce yield by 10%. Now, you can do the same thing in the Philippines, and they have done it with rice under controlled conditions where nothing is lacking for these plants, and the temperature is just going up and down naturally. And it turns out you get 17% loss per degree C increase. You can do the same thing in India in wheat, and you find out it's 15% loss per degree C increase in temperature. These are controlled environments where there's nothing else limiting. If there was water limiting, it would be even worse. If there was fertilizer limiting, it'd be even worse. Right? So this is kind of like the best case scenario. But if you live in the tropics and subtropics, you're well beyond the optimal temperature, so as you increase, yields just go down. Right? Especially important for all crops, but especially for wheat, rice, and maize. Okay. Here we go. Here we go. So the impacts of temperature. 3 to 4 degrees C increase, minimum reduction of 10% per degree C. End of this century, how much reduction we have? 3 to 4 degrees, 10% per degree? 30 to 40%, right? Under optimal conditions. No water limitations, no nutrients. Okay, so reduced yields of wheat, rice, and soybeans in the tropics, should be maize there too. Approximately 10% per degree C, and that gives you a 30 to 40% decrease in 2100 in India, Southern Africa, Middle East, anywhere in the subtropics between 35 degrees north and south latitude. Increased volatility in crop yield. So this is where, actually still I think most people think that the US is kind of immune to this for a really long time because we are close to that optimal temperature, right? Whereas in the tropics, you're already well past it, right? But it turns out that that's not the key. All right, so this is a typical thing you see for any species, even me, right? Where you can say, well, this could be like fitness of me, you know, like how good I do in life. And I have some optimal temperature. For me, it's probably more like 15 degrees Celsius. It's not, I wouldn't do too well in Tucson. Okay? Maybe I'd adapt to it. I mean, that'd be, yeah, okay. But for most plants, it's about 26 or 27 degrees Celsius is the optimal temperature. And if you get colder than that, it's not so good. And if you get warmer than that, it's not so good. And pretty much all things have this asymmetric curve where once you start getting warmer, it drops off really, really fast. And there's good reasons for this that have to do with basic physics and biophysics, I should say. Okay, so now I put myself in upstate New York growing up, and there's my average temperature, and there's the natural variability. I'm wobbling around, and you can see, even under a cold year, I get 90% of my perfect yield. And even under a hot year, I get 90%. So I actually don't see a big change in yield. Okay? Small. And you don't worry about it. Great. Okay, but now if I just warm up a little bit, and I'm living in the mid-latitudes, I shift myself out to here on average. And I still have the same natural variability, but now I get, if it's a cold year, I get perfect yield. But if it's a warm year, I get 0 yield. See the problem? So the volatility, not just because the mean is shifted, it's because the mean is shifted and you still have the same natural variability in climate, means that yield volatility is going to go through the roof. Okay, so this is a really serious problem for all of the breadbasket countries in the world, the US, China, Ukraine, Europe. Okay? They produce most of the grains in the world. Okay. Here's an example. Here's Iowa today. Okay? If they plant May 1st, you put in corn, and here's the average yield today, and this is like one of those histograms again. The most likely scenario is that you're going to get your average yield, right? Uh-oh. And there's only a really small chance that you'll get low yields. Okay, so let's summarize this. Today, if I look at the average yield, and I say, what's the average loss of the average yield? Well, it's 0, right? The average yield is the average yield. And I say, what's the odds of, say, experience a 10% loss due to the natural variability in temperature? And the answer is, well, I expect to see it every 9 years or so on average. The odds of seeing a 20% loss are every 25 years. The odds of seeing a 30% loss are every 50 years. You know, it's every 2 human generations. So you don't worry about temperature today, right? The volatility due to precipitation is much bigger than temperature. But now, let's go out here and we say, as you go out and you say, well, at 1.5 degrees on average above normal, the average yield is only 5% lower. That's not bad. And this is why, until really recently, we thought this was not a problem in the mid-latitudes. Even when you go out to 2 degrees warming, you're still only losing 10% on average. But let's look at the return time, how often you lose these things. So if you look here, it's say 1.5 degrees, which is what we expect in 2035. That's 20 years from now. You expect to lose 10% every 3 years and 20% every 14 years. If you go out to 2050, right, you expect to lose 20% every 2 years and 30% loss in your crop every 5 years. And then this is on top, this adds to the precipitation variability, right? This is in addition to what we already have in terms of, so you cannot do agriculture in the United States the way we do it today. No farmer could withstand this amount of volatility in year-to-year production and stay in business. Okay? In the United States. Okay. So one other temperature effect here is what it does to pest populations. And I'm just going to show you this slide really quickly. There's every year, you lose a certain amount of your potential yield due to bugs, eating your crop. In the United States, typically that's about 8% or so of your crop in maize, say. And that's a typical number for a developed country in the mid-latitudes, France, Ukraine. I think China's a little bit higher loss. If you just increase temperature by 3 or 4 degrees over the land, by 3 degrees global average, and you say, well, how much increase in loss will I have due to pests at the end of the century? And that's what's colored here. And red is a 40% increase. So I expect in mid-latitude regions, United States, Europe, China, basically, losses of wheat, maize, and rice yield to increase by 30 to 40% because of increasing pest pressures. Bugs do better under high temperatures in mid-latitudes. The other important point here, let me just work you through one plot here. This is the amount of yield we get per hectare, per acre, how much crop you get, how much grain you get. And this one is, help me out here, I can't see this close to the stage, maize, okay? So, for example, in the United States, we average 7 tons per hectare of maize we take off. And the other thing to point out here is that the size of this bullet is telling you about the total production in the country. So the bigger the bullet, the more of the world's grain they produce in that grain. So the United States produces the most corn in the world. China is second. What's plotted here on this axis is the increase in the loss of crop due to increased pest pressure. So the point here is that the countries that produce really high amounts per hectare and the most grain in the world suffer the biggest losses in pests. That's true here for maize, it's true for rice, and it's true for wheat. And these are for really basic metabolic reasons in ectotherms, cold-blooded animals, okay, which are pests. Right? Okay. So the percentage increase in yield loss is greatest where the yield is already the highest and most grain is produced in the world. Okay. So let's, I'm going to summarize those points and put a few more things on the boards we're pretty sure of, but are harder to quantify. We know kind of a minimum estimate under optimal conditions of a loss is going to be on the order of 10% or more per degree C increase. So many crops in the tropics and subtropics are already well beyond the optimal growing temperatures. So increasing temperature, we expect yields of wheat, rice, soybeans, maize should be on there as well, reduced by 10% per degree C of warming. Yield reductions of around 30 to 40% in 2100, that translates to that in India, Southern Africa, Middle East, pretty much anywhere between 35 north and south where you're going to grow these crops. By 2050, you'll have increased volatility of crops in mid-latitude breadbasket countries, the countries that produce most of the grain in the world. US, Europe, Ukraine, China. Loss of arable land due to salinization of groundwater. So as you increase sea level, if you're in a coastal area, you put more pressure on the water that pushes inland, and that's saltier water, so that the groundwater is more salty, and that's not good for a plant. So you'll lose some land due to that sea level rise. Water stored in snowpack will go down. And this is even if precipitation doesn't change. If the snow line, where it changes from snow to rain, increases, the area that you can actually capture snow in a mountain goes down. So this is particularly important in a place like the Sierra, the Cascades, where irrigation using the snowpack, the snow that falls, is really important for crops. Increased crop loss due to increasing pest pressure. We just talked about that one. Decreased nutritional content of grains. When you grow grains under higher temperature, the protein content of the grain goes down. I'm not going to try to explain that. Next week, Russ Munson is going to do a phenomenal job on this, and I'm going to leave it to Russ to explain that. But it's also true that when the protein content of the grain goes down, right, then the grain is more susceptible to disease. Now, increased disease transmission rates. Bacteria, viruses do well under high temperatures, right? So the transmission rate of diseases that affect these plants will increase. Okay, impacts of changing precipitation. By 2050, many in the subtropics will feel impacts of changing precipitation. We talked about rainfall in Africa, the Caribbean, Central America, the Middle East will be reduced by 10 to 20%. The frequency and duration and intensity of drought will increase. Flooding will increase in both the mid-latitudes and the tropics. Okay, so those are just the climate impacts we're pretty confident in. The impacts on crops are crop yields will be reduced, and in some places staple crops will have to be abandoned. I really want to talk about this, but I'm running out of time. Shorter, more intense monsoons. It's kind of interesting. This is not something that I think we understand well, but every climate model tells you the monsoons will be more intense. We understand that. There's just more water vapor in the atmosphere in a hotter climate. But what we don't fully understand is that everywhere we've looked, monsoons are shorter. In a place like Indonesia, the monsoon today is just long enough that you can plant two crops of rice. If you make the monsoon shorter, you can't. And that's what happens in an El Nino year. Like this year is going to be a really bad rice production year in Indonesia. Anyone got any money in this? Actually, not much rice is traded in the open market. But what happens then is you can't grow that second crop, and so you basically, food supply for the country goes down. Indonesia is the fourth most populated country in the world. Rice is a staple crop, and it's a poor place, relatively, right? So this is a big problem for Indonesia in 2050, not at the end of the century, but really soon. More nutrients will be leached from the soil. If you have really intense rainfall on drier soils, it tends to leach nutrients out more, and that's not good for plants, losing your food. Climate change will decrease soil organic content, which is also the food, right, for food for plants, and impact the soil biogeochemistry. And the last one here, which it turns out, for agriculture anyway, increasing carbon dioxide, people often talk about, well, carbon dioxide is a food for plants. Plants should be happy. Well, it turns out that, yeah, plants are happy, like weeds, right? So they compete for food with corn. And the other thing is you have the temperature effects associated with increasing temperature, and those are all on the downside. And very quickly you find out that increasing carbon dioxide does not give you this food for plants, right? It's a net loss very quickly everywhere on the planet. And there's many, many more impacts on managed ecosystems and wild ecosystems that Russ is going to talk about next week, so I won't go there. And besides, it's not my expertise. Okay. Let's go back and think about what this means for the food insecure, right? Go back to this picture. These are the places where you have the billion people on the planet that are malnourished today. These are the places where people really depend on agriculture for income, to buy the food, and to eat and growing the food. It's the places where countries have the greatest growth rates. Almost all of that extra 2.5 billion people that we're going to add to the planet are going to be added to those countries. They're poor, they depend on agriculture, and they're the regions that are most stressed by global warming, right? Just look at, right? So the estimates are hard to come by, but you end up with, sort of like another 200 to 400 million people that are malnourished, right? So this is not a problem that's kind of out at the end of the century. It's a problem that's like, 2050. It's a problem that, will I live to see it? Maybe. Certainly my kids will, right? It's only 35 years away.